Yeah, thanks for the kind introduction. Hi, everyone. This is Liangcheng. I currently in the software hardware co-design team in Microsoft Research Redmond. We're system networking researchers, and we came across this context of cloud-hosted financial exchange. It's my first time being to this conference. So today I'm going to present Cuttlefish, which is a fair by design cloud execution environment for algorithmic trading. So real quick, this here's sort of a simplified diagram showing a typical setup of today's on-prem exchange infrastructure. So here refer at market participants or MPs as the computer programs in low latency algorithmic trading. So it usually co-locates market participants in the same physical facility and use layout fan-out switches, and often use also they try to do equal length cables. And then to ensure fairness, the central exchange server or CES releases market data simultaneously and then expects them to reach each market participant at the same time. So for the inbound direction, it processes trades at the order of its arrival, as we can see here. Okay, so really the goal of this work is to explore the viability of hosting financial exchange in the cloud. So we're inspired by the recent years' interest in moving exchanges to the cloud. So this includes major exchange service providers, but also cloud providers like Microsoft, Google, and so on. So moving to cloud promises a bunch of benefits. For example, it can bypass the logistical hurdles to install, maintain on-prem hardware. It can improve system scalability, also reduces the barrier to entry, and so on. So moving to cloud, however, is complicated. One of the key reasons is performance variation. So I'll illustrate what I mean. So here's a diagram shows a setup of cloud host exchange where all system components are controlled by the trusted exchange service provider and also co-located in the same cloud region. So similar to on-prem setup, you have a CS server, but unlike the on-prem setup here, users can simply run the virtual machine or VM in this case in the same cloud region as the CS and then run their algorithmic trading programs or market participants. So in the cloud networks, the underlying paths can be different and the latencies are constantly changing. So as a result, trades may arrive earlier as some market participants, leading to earlier trade submissions, even if two market participants perform the equal amount of computation. So this is really bad because let's say if two market participants both want to sell as quickly as possible, but now who wins is really dependent on luck. So recent work have attempted to address this effect. So just to give a very high level intuition. So CloudEX, for example, tries to synchronize the clocks of all system components. They buffer the market data and then they release them at some scheduled deadline. So in this case, if the latencies are smaller than the deadline values, the release buffers here can send the market data simultaneously. Unfortunately, as we know, that perfect clock synchronization is really challenging in a cloud environment. And besides, even with perfect clock synchronization, due to unpredictable latencies, it's also difficult to set the right deadline values here, as there's always a trade-off between how long you wait versus the degree of fairness. So there's a more recent work called DBO in SICON 2023. So what it does is it's try to introduce this notion of logical clocks. So basically every time there is a market data, the local SmartNICs will measure the time it takes for a market participant to respond and then tag the outgoing trades with the response time. So now the CES will prioritize trades that has a smaller response time rather than whoever arrives earlier. So unfortunately, DBO only guarantees fairness for a specific class of trades, namely the trigger point-based high-speed trades, but it doesn't handle more generic trade patterns. And it also neglects the latency variances between the controlled SmartNICs devices and the market participant VMs, which can also cause unfairness. So Just to step back a little bit, even if we solve the problem of communication fairness, in the end, there's also other sources of unfairness that are difficult to control. So things like noisy neighbors or thermal fluctuations and so on. So to illustrate, we actually ran a simple micro benchmark where there are two identical trading algorithms running on two VMs of the same configuration. We trigger them with the same string of market data in parallel and then measure their execution time differences. So the figure on the right basically shows the result for different virtual machine types indicated by the x-axis. Even in a single tenancy case, as we show here, this F72 instance, where here 72 represents like number of CPUs allocated for this VM. So in this case, it prevents collocation to the same machine. So even in this case, and we use the same strict scheduling policies, things like pinning the cores and using highest kernel scheduling priority and so on, we can still observe both variability and bias between the two executions. So in this work, we're really interested in exploring the limits. Fundamentally, can we eliminate these variances that come from the cloud infrastructure? So in other words, can we provide sort of a execution environment where the outcomes of the races is not dependent on the lucky or unlucky performance fluctuations of the underlying infrastructure? So our approach is called Cuttlefish, which is a fair, predictable execution environment for cloud-hosted financial exchange. So it prevents user abstraction that basically abstracts out the variances in the underlying cloud environments in the cloud networks, but also extends the fairness guarantees end-to-end to the underlying hardware. So I'll walk through each of them in the next few slides. So basically, I'm first going to talk about the conceptual foundation of Cuttlefish, and then I'll walk through some of how Cuttlefish implements the abstractions, and then talk about some of the experimental results on commercial cloud platforms. So let's take a step back and reflect on the fundamental model underneath. So as here we show three nodes like CES, Central Exchange Server, and also two market participants. So now the walk clock timeline goes from left to right. So now whenever CES sends market data to market participants, as we know that even for the same market data, it's very difficult to ensure that they are delivered at the same time. And there's always this delta time difference in the arrival time. So in other words, truly simultaneous market data delivery is hardly feasible. And similarly, when it comes to code execution, even if two market participants have the same piece of code, the execution time can vary. And this is true even with the same hardware. In fact, it's not uncommon that the same piece of code can take longer or shorter on another machine to run because of subtle differences in thermal conditions and so on. We actually showed some of those in the earlier slides as well. So as we can see that achieving synchrony in communication and computation is really challenging in real time. So Cuttlefish takes a different approach, which is to explore the virtual time domain. So let me walk through this. So let's imagine that now every market participant now has a virtual timeline. So we could define each unit of virtual time as some equal amount of work. And now for execution fairness, we could advance the virtual time based on the actual amount of work rather than the elapsed real time. And by doing so, for the same piece of code, we can always end up advancing equal amount of virtual time. And similarly, we could achieve communication synchrony in virtual time domain. Basically, for each market data, now CES broadcast to all market participants based on the same virtual time. So this is feasible because, oh, some animation is going wrong. Okay, so this is feasible because in virtual time domain, one can freeze or advance the time accordingly. So I hope this is conceptually straightforward, but how to implement that in the real system? So our key idea is to introduce a platform-agnostic intermediate representation, or IR here. Here we pick the eBPF instruction set, and then we instantiate the virtual time unit as a primitive eBPF instruction cycle. So there are three primary components top-down. So first, market participants would express the trading algorithm and produce the IR, in this case in eBPF. And then Cuttlefish will track the virtual time cycle efficiently. And finally, the runtime architecture will handle the execution of trading algorithms. Let's first take a look at the Cuttlefish programming abstraction. So here's a simple pseudocode for a naive trading algorithm. So the user only needs to include a single header file, excuse me, which includes all the APIs needed. Now the user can process the subscribed data and then submit trades at any position in the code. And if the program wants stateful invocations, market participant can also interact with the memory and runtime through the provided KV store APIs. So this interface is quite expressive. In fact, we were able to write a bunch of commonly known technical analysis indicators with this interface. So what happens afterwards? So after user expresses the trading algorithm using some language front end, in this case, we're showing a case with C, but the user first needs to compile it into some COM-IR or EBP, in this case, in eBPF bytecode, and use it as the input to the Cuttlefish platform. And then Cuttlefish will first verify the program and then performs various instrumentation operations, including virtual time tracking. And finally, it will it will convert the bytecode into some native machine binaries, and let's say it's S86. And then note that here the virtual time tracking and the execution is decoupled. Cuttlefish uses the COM-IR to fairly deterministically track the virtual time cycles, but it executes the code in native hardware to obtain close to native execution performances. So as we mentioned, one crucial operation is to track and advance the virtual time. So to do so, Cuttlefish breaks the user bytecode into basic blocks, where each block is a straight line instruction sequence without branches. And then the JIT translator would just insert native hardware instructions to advance the virtual time counter based on the virtual time cost of eBPF instructions involved. And by doing so, the execution runtime can track the virtual cycle without interrupting the ongoing execution. So this approach is really similar to what people did before for binary rewriting and so on. So now, when it comes to communication, before multicasting market data, the CS will first assign a delivery virtual time. So each market data will piggyback this timestamp, and then the release buffer at each local server machine, which also maintains the virtual time of each local local market participants, will then forward the data based on the individual market participants' current virtual time. And by doing so, each market participants will get the data at the same virtual time. So this ensures fairness, but there are cases to handle when assigning the virtual time to ensure that the system will progress efficiently. So in the interest of time, we don't dive into details here, but basically the paper contains more details like how it does the virtual time assignment algorithm and how it handles failures and so on. So now I want to walk through the sort of a more complete picture of the end-to-end runtime execution workflow. So here CS first assigns a proper virtual time and continuously multicast the data with a delivery virtual time. So this data is handled by the dispatcher thread on each local machine and then which basically produce the commands for each worker thread. And then upon dequeuing a command, the worker thread will first update the virtual time based on the release virtual timestamp, and then executes the instrument assembly that we talked about earlier. And during the execution, the instrument code blocks will advance the virtual time without interruption. And whenever the execution hits the instructions that actually correspond to trade submissions, the worker thread will submit trade with the latest virtual time. And then the aggregator thread will pull the trades from the buffer, sort them locally, and then batch send them to the CES, which process trades and update like the limit order book and so on. So here we focus on one virtual machine server, but as we can imagine that this infrastructure can scale out correspondingly to multiple machines. So now finally, we prototyped and evaluated Cuttlefish on today's public cloud platforms. We first compare the effects of Cuttlefish with existing ordering schemes. So note that the CloudEX and DBO that we talked about earlier, as sort of related work, they either require high resolution class synchronization or SmartNIC supports, which are both hard to replicate in our cloud environment. So we use a process called response time ordering to study their behaviors. So you also include FIFO ordering, which is kind of straightforward. It's just process trades according to their arrival times. So in this setup, we have two VMs. Market participant A will execute more instructions than market participant B, and the market data is delivered every 100 microseconds. So the metric we use here is similar to prior work called fairness ratio, which basically indicates the percentage of trades that are ordered correctly. And because in this case, market participant A is always executing more instructions than B, in theory, should be always ordered later. So now let's first look at a case when two market participants, two VMs are using the same type of machines. So in this case, the x-axis is the instruction count difference of the two market participants. We can see that the FIFO has a very low fairness ratio. I'm not sure if there's a counter pointer here, but we can see that FIFO has very low fairness ratio because the market participant A is running on VM, which has much higher round trip time, RGTs, compared to that of market participant B. So the response time based trading is response time based ordering is kind of more resilient to this effect. But even so, it's still not perfect. So if we, even if like in this case, we look at this last group of bars here, on the right. So even if in this case, market participant A executes far more instructions than market participant B, which we would have thought that the response time based ordering should result in correct orderings, but it still has a small percentage of trades that are not correctly ordered. Now, if we look at a case when they have they're using different VM types. In this case, it's not just about the disparities in the network, but also they're using different processors. In this case, we can see that the response time based ordering is also suffering. As we can see here, the values are much lower as well. We also evaluate performance, cost of Cuttlefish for fairness, focusing on the end-to-end latency. So the table here basically compares Cuttlefish end-to-end latencies against the max RDT across various percentiles. So here max RDT represents the maximum latencies across VMs corresponding to the same market data. So we can see there are latency discrepancies, and these are attributed to the data flow operations of Cuttlefish, including things like batching, ring management, virtual time assignment, and so on. But despite that, Cuttlefish trades some latency for fairness, it still closely approximates the limits of the underlying infrastructure. Again, like the paper has more details on the results, and feel free to check it out. To summarize, Cuttlefish presents a fair, predictable cloud execution, cloud-hosted exchange platform. So it abstracts out the variances of the underlying network communication and computation hardware. So the outcomes of the races are not dependent on the lucky or unlucky performance variations. So with that, I'm happy to take any questions.
For the presentation, do we have any questions in the audience?
Thank you for the talk. I did not understand your definition of fairness here. Can you go back and you said it has 100% fairness, but I have no idea what that means.
So which slide here?
No. This is in the numbers. You said somebody executes 50% more instructions, but they under this scheme it's 100% fair. What does that mean?
So you mean in the evaluation, which is
in the evaluation?
Oh, yeah, okay.
The metric of fairness, unless I missed it, is not.
I see. So so the goal of this work. So I think fairness is kind of maybe it's not the exact word here, but basically we're trying to provide an environment where if you have competing market participants, right? So the race is not dependent on let's say this process is faster, slower, or having different thermal conditions, or the network is faster and slower. So and if we talk about fairness, it's if one market participant has one more instruction than the other one, it should be ordered for the same market data. It should be ordered later, if that makes sense. This is a conceptual explanation.
Sure, right, but a data race could happen when, for example, you could wait a second, have slightly more information than the person who submitted first, but and then process the same amount of data. But just because you are faster, you will already have an advantage here. So even if I understand virtual time, which should be something like number of instructions executed, right? Even in this case, fairness I don't think is capturing a true notion of we all have the same information. Does that make sense? I don't know. Maybe that's just like a weird distinction in the model that I'm not understanding.
I see. I can take it offline.
Yeah.
We can
Okay.
chat. Yeah.
Be curious. Thank you.
Yeah.
Do we have any other questions? Also, in the meantime, the next speaker can maybe go up already. One second, I think for the recording.
I think it's just a follow-up. Yeah, what if you thought about different notions of fairness? Yeah, what are the possible ways in which you could think about fairness? As I understand, yes.
So I mean, this is like a huge design space, but I think prior work, if I start with simpler cases, so you could define fairness as something like, you know, whoever arrives, if like fairness being like, okay, if the cables are of the same length, like connecting to the market participants, that should be one definition of fairness. But the other one could be defined based on response time, which is on the right-hand side here, where it's one should be ordered earlier if its response time is smaller than the other one. That could be another form of definition, if that helps a little bit. Okay.
Okay, are there more questions? Oh.
I'm just curious if it is deployed somewhere.
No, this is right now a research prototype. We did talk with relative related people, but right now it's still ongoing. Yeah.
Okay, thank you.
Thank you.